forced to spend my weekend to set your final exam. Yes, I was called on Friday night by your program director, Mr. Percival Stewart, advising me that the module comes with a final exam and that it was long overdue to be submitted. And that was because they did not advise me, so I might have missed the date. So he called me Friday night and said, "Listen, we have to get this thing sorted out so that by Monday it can be handed in." So I spent my entire weekend setting what ought to be your final exam for the module, which is scheduled to be sat in May. I'm not too sure what date exactly. I guess that depends on the university. But what I'm sure of is that the exam is already set and submitted for review and ratification by the university. So yes, the idea of avoiding a final exam and go for a project or a take-home assignment is not to be. The Mr. Stewart advised me that the exam comes with the mode. That's the mode that they use. It comes with it. All right. The students before did it, so you will have to do it also. All right. So it will be an exam. So I spent my weekend doing that and didn't get to touch your assignment because of course I can't dedicate my entire life to UTech and its work. I have to do other things, including family matters. All right, but I will find some time and finish marking them. I mean, uh, not to worry. The I actually set my exam from a past paper, a past exam that Mr. Stewart shared with me, and from what I see, from what I saw, and from what I know, I put, if you're a well, the the assignment you did, it have you well on the way to pass your exam already, along with what we're doing now with beams. And of course, when we do timber, because of course the course covers structural steel and timber. Timber is going to be narrowed down to just timber columns and timber beams. Nothing about tension or anything like that. All right, and nothing about connections. However, however, for the steel part, after we finish shear today, then tomorrow we'll look at simple connections, and that would have wrapped you up completely for the steel part of the program and also for the steel part of the exam. The big question is though, I'm almost sure people might want to ask, sir, is there going to be formula sheets? And the answer is yes. Based on what I saw in the previous exam, there's a formula sheet. Not all the formulas are there. There are some simple formulas which you might be which you might have to know for yourself. But yes, the substantial ones are there, and all the tables and graphs that are required to do the exam are provided. So again, class, people escape having to be scrolling up and down in this big manual because we actually take out based on the question we set, we take out the sheets from that manual that you will have to go to. So we actually simplified for you. All right. So even though the exam might have 20 pages, from page 6 and to the end is actually formula sheet plus tables and graphs. How does that sound?
Sorry, question.
Uh-huh.
Somebody typed in the chat. They're asking if it's face to face.
If it's face to face,
Yeah.
um, I would imagine so. I didn't confirm that with Mr. Stewart.
Sure.
What I
Yeah.
know is that the exam is for 3 hours. Huh?
All right. Second question, sir. Would it be possible for you to share those the formula sheet with us before the exam, so we know
Uh-huh.
what we need also know what we need to memorize and what would be provided for us?
No, but you're basically having to share the exam with you.
No, no, no. The formula sheets or the formula. You don't need to share the
Actually,
graphs
no,
or
man,
anything. The
all right.
equations.
Whatever formula is on the sheet are actually in the books. But all right, but I'm not gonna share it. Right? I'm not gonna share it. What I say to you is that we will do enough examples which will prepare you adequately for the exam.
All right,
You
sir.
can
That's good.
understand it? Huh?
Sure. Yeah, that's good, sir.
All right, fine. So what I need now, what I need now is for the group to allow us to be able to cover the content in time. So we have some a class or two to go over to do some just work examples of all the aspects we've covered. And trust me, if you don't miss that, and if you come to those sessions and grasp, then you're on your way to scoring full on the exam. Now the exam is simple. It's 6 questions to answer. Five or let me see. I would open another computer so you don't see it. But it's 6 questions to answer. It's 6 questions to answer. Good. It's 6 questions to answer four. That means you have options. You have options. 6 questions to answer four. That means you have two you can throw away. All right. Not to say you should not study all topics, because some questions might actually have a crossover between the hybrid, a crossover between steel and timber. All right. And that is because we know that people might want to escape a particular topic. So actually make a hybrid questions to cross over both of them. So you can escape it. All right. But yeah, six to answer four, and trust me, they are simple questions. I can tell you from now. I can tell you from now. Even the questions to design a column, it won't be anything to do with iteration. There is just 3 hours. You don't have time for that. Trust me, iteration can take up time. So the simplest design method that we did by just going into the table and find a column. That method. So right away I give you a clue. Nothing to do with no iteration and assume FCR and go again. No. That can be that is too timely. You have 3 hours to do 4 questions. No time for that. Which is why we provide all the tables you need. All right. So it's a quick method of going into the table to select a column. All right. The sketches are rather simple and the numbers are easy to work with. Like I said, you are on your way to pass this exam. Trust me, if you should sit this exam now, you wouldn't get full mark because you haven't done timber, but you should be able to pass it. You should be able to pass it. All right. All right. Any more questions about this exam? Don't worry about it, man. Easy. Very easy. Even formula sheet that have nothing to do with steel or timber is there. For people who don't know to calculate moments and shear. You actually have a formula sheet to show you how to calculate the moment of beam with simple with point load and uniform distributed load. That means, yeah, very good. Any other question before we move on? No other question?
Sir, I was logging out and sir, but sir, what you just said about the exam? Sorry.
Huh? What I said about the exam?
Sir.
Huh? Go again. I didn't get your question.
So I'm having a Wi-Fi problem, sir. What did you say about the exam, sir?
I'm saying the exam is pretty easy. Based on what we do so far and what's on the paper, if you were to sit it now, you wouldn't get 100% because you wouldn't have done timber. But you should be able to pass it based on what we did. I was saying to the group that even the design question we are asked to design a column is nothing to do with iteration and going 1, 2, 3, 4 steps. No, it's the simple method of going into the table and find a column that fits your load. The 2-step one. Once you're able to calculate the maximum load from the load you're given and find PU, and you know your length of your column, you go into the table and find a column that suit that. Nothing to do with try FCR equals this. When you don't work, you reduce FCR. No, nothing that's too timely for an exam which is to be finished in 3 hours. So everything is the simple method, including the beams. Is going to the table to find results. Nothing too laborious. All right, but we need to finish up with shear today so that tomorrow we can spend the time doing simple connections, because there are questions out there with simple connections. And I did say that we can't do steel without doing connections. Connections being welded or bolted connections. All right. And by connection we don't mean base plates and moment connection. No, we mean simple connections subjected to just shear from tension. So we'll be looking at connections of tension members. All right. That's what the course really cover. For timber, for timber, it's really timber columns and timber beams. Simple design of timber columns and timber beams. Of course, there's going to be a relationship between what you did in steel and color, because the same critical buckling and the same effective lead factors, they come back into being what we do in timber, what we do in concrete, because the same principle. Right? So you'll be able to relate to it quicker and easier, because you would have previous knowledge of what does effective length mean and what does effective length factor means. All right. Good. So can we move away from exam now?
So just one more thing, if I may add, along with us going through the questions at the end of the semester, could you just prepare like a mock exam so you can just go through that?
Go again.
I'm saying if you can prepare a mock exam.
All right. So I did say we are going to finish. I am going to make sure the content part of everything is finished, and we have a 1 or 2 class remaining, and we'll be doing just questions. Having done that, trust me, you basically did the exam but with different numbers. If you understand me.
Okay, sir.
You understand? I'm going to do like a revision, an in-class revision with the questions geared towards preparing you for the exam and nothing else. All right, but you have to make sure that you play your part. Come ready to participate and come in early, so that we can get as much done in that little time. All right, but don't worry, we'll get that out of the way. All right, so exam talks behind. Let us. All right, fine. So you see my screen, all right?
Yes, sir.
See my screen. All right, so very short. We can get through this and a couple of examples. Easy. All right, fine. So the last part of what we'll be doing for beams, and I mean, I did say that we'll be looking at deflection, but based on the exam which we have there, deflection does not play a part. So I won't bother to get into deflection as part of your content. That is something that you can actually learn on your own, especially if you plan to go into designs. But deflection comes after this 5.8. It comes 5. Let me tell you where it comes. 5.9. Right? See the deflection come 5.9. Right? But we are going to be stopping at 5.8, and only the simple part of 5.8. We're not going to be looking at block shear. That's when we start to do moment connection and all that with bolts tearing out piece of your metal. We're not going to get into that yet, because we're not doing that kind of a design in this course. Maybe need a structural design 3 for that. All right. So I am reading from the principal textbook, Steel Design 6th edition by William T. Segi. And we are still on chapter 5 because of the beams and bullet point 5.8. All right. Now, this part here is just theory or like a narrative behind shear for people to appreciate what is shear before we start to look at all this expression, formula, factors, numbers, and whatever. All right. So allow me to read so that we can grasp some knowledge before. Beam shear strength is covered in chapter G of the AI SE. Again, this orange color book. I can't overemphasize this book that I gave you. All right. So all that we're going to be looking at for shear is covered in chapter G. All right, and this lucky this time the bookmarks or the links are live. So when I click on it, it comes up. All right. So this chapter deals with shear. See them there right away. All right. It says here, design of members for shear. Both hot rolled shapes and welded build-up shapes are covered. All right, fine. So there are two principal types of members: hot rolled, which are the ones that we have been recommending, the double shapes, or the H shapes, or the S shapes, or the M shapes, or the channel, or the angles. Those are all hot rolled. Or you also have built-up, which are made from welding plates together to get the same form. You weld 3 plates together to get the same I or W. All right. So both of them are covered really. We are interested, however, in just the hot roll one, the one in the manual. All right. We discussed hot roll shapes in the present chapter of this book. We are going to be doing the same thing too. And built-ups will be done in chapter 10. We won't be looking at built-up. All right. The AISCE provisions for hot roll shapes are covered in section G2.1. All right. So it's G2 I shape and right and point 1. All right. So it's referring to right here. All right. Before covering the AISCE provision for shear strength, we will first review some basic concepts from mechanics of materials. Consider the simple beam in figure 5.17. This figure right down here. So this is a simple supported beam with a pin support and a roller support there, and it is subjected to 1, 2, 3 vertical forces, point loads. It says at a distance x, see x here. Come on, x. From the left end at the neutral axis of the cross section, the state of the stress is shown in figure 5.17D. 5.17D. This is this. At any distance x, the state of the shear stress is shown, right? Because this element is located at the neutral axis, it is not subjected to flexural stress. No stress from bending. From elementary mechanics of material, the shear stress is given by Fv, which is shear stress, symbol for shear stress, divided by Vq over Ib. Now this is general information. Let us now look at the definition of each of these terms or each of these unknowns in this expression. Fv is the vertical and horizontal shear stress at a point of interest, like this point x, right? V, the vertical shear force at the section under consideration. The vertical shear force as provoked or as induced by these loads, whatever the values are. So you take a particular location and you can find the shear stress at the location, right? Q, the first moment about the neutral axis of the cross section between the point of interest and the top or bottom of the cross section, and I is the moment of inertia about the neutral axis. B is the width of the cross section at the point of interest. Right? So this is a general expression for how to find shear stress using up all this illustration there. Right? However, we're not too interested in this shear stress thing. So we go further. And this is really showing the shear stress diagram. For argument's sake, if this is a cross section of a beam, then this is what the stress would look like. Because this flange is so thin, TF, then the stress in the flange is just this little piece. Because the web is this deep, then the shear stress will do like this in the web, and then go into this flange again and do this. Right? So this is just to show how the stress distribution. This is the zero line really. This line here, if there were to be a line right here, then stress at that equals 0, and the stress increases as we move from left to right of the line. As we move towards the right of the line. So this is 0, and then B start to take on a value. That's what that's go with it. That's what that means, really. All right. Equation 5.7, which is the one above this one up here. Equation 5.7. Scroll too fast. Equation 5.7 is based on the assumption that the stress is constant across the width B. Right? And it is therefore accurate only for small values of B. For a rectangular cross-section of a depth D and for width B, the error for D over B equals to 2 is approximately 3%. Right? For DB equals B over B equal 1, for a perfect square, the error is 12%, and for D over B equals a quarter, it is 100%. So of course there are limitations. The assumption that the stress is constant across it, right, is a limitation. And this was investigated and written down by these fellows. Right? Thanks be to them. We don't have to get into all this. They use all this information and develop equations for us to work with, which is where we want to get. For this reason, equation 5.7 cannot be applied to the flange of a double shape in the same manner as for the web. So we could not have applied this crude formula up here to an I section, because there will be different things happening in the web and the flange, respectively. So they are saying that equation is not valid for a W shape. All right. Superimposed on the actual distribution is the average stress in the web, V over A. Oh, sorry. I should have started right here. Figure 5.18 shows the shear stress distribution for a W shape. 5.18, which is this. All right. I've looked at it before. Superimposed on the actual distribution is the average stress in the web, V over AW, which does not differ much from the maximum shear stress. Clearly, the web will completely yield long before the flanges begin to yield. Because of this, yielding of the web represents one of the shear limits. Taking the shear stress at 60% of the tensile stress, we can write the equation for the stress in the web at failure as follows. So now, this is the equation that we are most interested in, because this is dealing particularly with W shape or I beams, which we work with, right? Shear stress is equal to Vn over AW, right? And that is equal to or approximately 60% of the yield stress of the steel. Fy, we already know it's yield stress. I don't want to be 36 grade or 50 grade or 65 grade. Right? The 0.6 is because they have departed from saying that this yield stress is 60% of the tensile yield stress. All right? Where AW is equal to the area of the web that we can find because we know the web thickness and we know the depth of the beam. The nominal strength corresponding to this limit state is therefore Vn is equals to 0.6 FyAW. This is the general equation class, equation 5.8, and will be the nominal strength, shear strength, or shearing strength, provided that there is no shear buckling of the web. Whether that occur will depend on the ratio H over TW. H is the height of the web. TW is the thickness of the web. The width to thickness ratio of the web. All right, the slenderness ratio of the web. If this ratio is too large, that is, if the web is too slender, class 1 what slender means already, the web can buckle in shear, just like columns buckle because of slenderness. The web can also buckle in shear, either inelastically or elastically. All right. So this is the general equation. All of the equation will be formed based on this. All right. Now let's look at the specifically at the AISC specification requirement for shear. For the LRFD, for the load resistance factor design, the relationship between required and available strength is VU should be less than or equal to phi VN. VU. What is VU, class? VU is nothing but the maximum shear acting on the beam from the load the beam is carrying. That's the ultimate shear, VU. That's the shear you'll get from your 1.2D plus your 1.6L. All right? VU equals the maximum shear based on the controlling combination factor. And phi V is the resistance factor for shear. We have a resistance factor for tension. We have a resistance factor for compression. We have a resistance factor for bending. Now we have resistance factor for shear. All right? If you look at this equation, class, it's always going to be this almost the same. Just that we change from M now, so because it was normal. For bending, it was MU should be less than or equal to phi M, MN. Now we move away to shear, it becomes V. When we're doing compression, we add P. PU should be less than or equal to phi C PN. So right, so it's the same, this equation remains the same. It's the requirement for strength. Similarly, for the allowable stress design or ASD, the relationship is VA should be less than or equal to VN over omega V. Again, class, VA is nothing but the maximum shear force or shear based on the controlling combination of service loads, and omega V is the shear factor or the safety factor for shear. All right, those factors you will soon get. All right, we will go up on them. As we will see, the values of the resistance factor and safety factor will depend on the web width to thickness ratio. All right, these values will depend on this ratio. Section G 2.1 of the specification, this section, see them there? This section, see the factors in there? All right. So for those who want to learn to jump between documents to find factors, it's quoted. All right. Section G 2.1 of the AISC specification covered both beams with stiffened webs and beams with unstiffened webs. In most cases, in our cases, hot roll beams will not have stiffness. All right. So we are going to be dealing with unstiffened beams, unstiffened web. We're not going to put any stiffness to our webs. And for the benefit of those who are trying to figure out what are beam web stiffeners. You see my screen, class? Are you seeing the screen?
Yes, sir. Yes, sir.
Yes, sir.
Yes, sir.
All right, I'm trying to get the largest possible image of this. All right, fine. So all right. So this beam to the top right hand corner right here. These two vertical members are what we call stiffeners. That's when we have to put in some plate and weld them to the beam so that the web does not buckle. All right. So those are what we call stiffeners. The elements in the manual do not have this. We have to introduce it. So without it, it's referred to as unstiffened webs. When we are interested in webs without stiffeners, unstiffened webs. All right. This for this part of it right here, for people who are trying to figure out what is web buckling, this is a perfect example of web buckling. The extreme right image at the top, where you see the web bend on like that, it's that's what we refer to as web buckling. So to prevent web buckling, sometimes we introduce these stiffeners. So the stiffeners brace against the web, so the web cannot bend out, right? So that was just to give an illustration of what unstiffened and stiffened web is. But we are focused on the sections in the manual which do not come with stiffeners, and we want to work with them unstiffened. All right, fine. In most cases, out-roll beams will not have stiffeners, and we will defer treatment of stiffened webs until chapter 10. We are not going to chapter 10, so we won't be looking at stiffened web. The basic strength equation is, all right, so this equation is now moving from up here to something much more complex now. And this is because we know to start to take into consideration the fact that the web can also buckle. So the equation becomes Vn, which is the nominal shear, is equals to 0.6 Fy AW CV1. Let's define what each of these terms mean. AW is area of the web, and that approximates to the depth of the beam times web thickness. It says here D is equal to overall depth of the beam. The overall depth of the beam you will know, class, because it's in the manual or it's also given in the beam designation. W10 by 15 means the beam is 10 inches, right? So that's D, right? CV1 equals the ratio of critical web stress to shear yield stress. CV1 is a ratio or is a factor. So we must be getting these factors from somewhere. Let's look at how we arrive at these factors. All right. The value of CV1 depends on whether the limit state is web yielding or web buckling. So like with columns on a compression, there is yielding and there is buckling of the web. All right. Because remember now, shear stress acts vertically on the web. So the web will tend to buckle. Shear stress is like a point load on the web. All right. If you want to form a relationship between compression and buckling with shear. All right. It says here though, first case 1, for out-rolled eye shapes with height divided by web thickness less than or equal to this factor. 2.24 is a factor class. E is the modulus of elasticity, which is 29,000 kSi. Fy is the yield stress depending on the strength steel you're using. If this ratio is less than this, then the limit state is shear yielding, and CV1 equals 1, phi v equals 1, and omega v equals 1.5. So class, here it is. The first thing we do, we have an element, we check this ratio. If this complies, then we use these factors in this equation. That's case 1. And that's when you have the limit state of yielding. All right. It says here most W shapes with Fy less than or equal to 50 kSi fall into this category. It didn't say all, but most. All right. It says no for all other eye shapes and channels. If they didn't fall in this, for all other ones that falls outside of this, phi v is equals to 0.9 and omega is equals to 1.67. This number keeps coming up. 1.67. All right. So that's case 2. So case 1 is when you try this and it works. then this applies. For all other, then these apply. All right. And look, and you have to calculate CV1. In this case, CV1 was 1, but now we have these, but we have to calculate CV1. And CV1 is determined as follows. For H over TW is less than all of this, there is no web instability, and CV1 equals 1. All right? So the first thing is to check this. If this comply with that, then all this. If this doesn't comply with this, then we are in this case. And these apply, but we have to know calculate the value of CV1. To calculate CV1, we have to know compare that same first value we got with this. If this complies, then CV1 equals 1. This corresponds to equation 5.8 for healing. Because it's equal to 1, you come back to the same equation, 5.8, which is this. Because that value of CV1 becomes 1. All right? However, if this H over TW is greater than or this, then CV1 is calculated as follows. And for all of these two cases, class, the value of KV equals 5.34. The value of KV is for unstiffened webs. Web stiffness are covered in chapter 10. We're not going to chapter 10. So we are stuck with this. And class, that is it really. For sure. Nothing more to it than that. There's nothing to it than that, really. For sure. Unless you want to look at the allowable stress formulation. All right? Which converts forces to stresses. All right. Now let us look at this word example so that people can start appreciate more what we did. All right. I'm going to see if I can bring down some things so that they make more sense to us when we're doing it. Jessica, go away with that thing. Yes. Bring it up. All right, I'm trying to make sure that we have change code. I feel color. All right, good. I'm trying to bring down some information so that we don't have to be scrolling too far. All right, so that is that. Then next check we have to do. Fine. So if we check that on this, then this happens. So we need this also. All right. So we need that. If that happens, then this. If that happens, then this. Right. Then that. All right. Good. All right. First, I'm trying to. All right, so class, let's look at this example, and I guarantee you that we'll appreciate all the narrative above. It says here, check the example. Check the beam in example 5.6 for shear. Also, we need example 5.6. 5.6. This is it. All right. So we need this down there also. For those who are going to be writing off, all right, fine. I'm going to put 5.6 above so we can check it. All right. So this is example 5.6. All right. It says here, check the beam in example 5.6 for shear. 5.6 reads thus: a simple supported beam with a span length of 45 feet is laterally supported at its ends and is subject to the following service loads. All right. So the beam is 45 feet long, and the dead load is 400 pounds per foot, including the weight of the beam, and the live load is equal 1,000 pounds per foot. The steel is a grade 50 with a FY of 50 KSI, and the beam is a W14 by 90. That's all we need to know. All right. We're going to check that beam for shear. All right. Now, the first thing, class, the first thing we're going to be checking for is the slenderness of the web. Slenderness of the web. All right. From the dimension and properties table in the manual, the web width to thickness ratio of a W14 by 90 is fine. So we need to go now to the table. We're looking for W14 by 90. So quickly, I am jumping across to the manual again. I'm looking for W section, and it's W14 by 90. I find, so I'm at W12, 14. I find. So looking for W14 by 90. I seem to be not too far from it. W14 by 90. Right, this. W14 by 90. W14 by 90 is this one. All right, what do we get from the table? W14 by 90. They have, okay, fine. On the properties, in the properties table, this one, properties, the same W14 by 90, which is this one, we don't even have to calculate anything for ourselves. They already give us this column, H over TW, this one, 1, 2, 3, the third column. All right, this one. So I move down until I come to that. And see, it's the value below. It is 25.9. H over TW, 25.9. See there? H over TW, 25.9. So that's a given in the table. It's a value. All right? So we have that. What should we do with the class? We should compare it to this. It should be compared to this. It should be compared to this. And the web area AW is D times T. D is 14. Like I said before, D is the overall depth of the beam, 14 inches. And what's TW? TW we can find from the manual. TW is up in the dimension part of the table. So TW is in this column. Web thickness, see? Web thickness, TW. And that is 0.44 inch. So that class is what the multiplied here. So the area of the web equals the depth of the web, or if you want to call it length of the web, times the thickness of the web, which is 14 times 0.44. Both of them are tabulated, but we know the depth because it's a W14 element, and the 0.44 is from the table directly. Are we all following? Class? I'm gonna sleep. Class?
Still here, sir.
You following?
Yes, sir.
Good. So the check is to check if this is less than this. So calculating this numerically it works out to be 54. Again, it's a ratio. There's no unit to it. So we compare this with this. Because this is smaller, it says since that is less than that, then the strength is governed by shear yielding of the web. The web does not buckle. Remember, it does not buckle. So it says shear yielding. The web is going by the strength is going by shear yielding of the web, and CV1 equals 1. This is what this says. For case 1, for outroll I shapes, if this complies, then the limit state is shear yielding and CV equals 1, phi v equals 1, and omega v equals 1.5. So let's see what I'm doing. And as pointed out in the specification note, this will be the case for most I shapes with this. And the nominal shear strength is given as this equation. Nominal shear strength is equal to 0.6 Fy AW CV1. Fy is 50 because it was given. 50K size steel. AW we calculated because the area of the web, 6.16 square inches. And CV equals 1 because this comply, hence there's no buckling of the web. So the nominal shear strength is 184 kips numerical. All right. Now, the next thing is so this is nominal. What we really want is to be able to make this comparison. We want to be able to make this comparison class, this one. VU should be less than or equals to 5VN. So far, we have VN. We have VN. That's what I calculate just now, 184 point whatever it is. 184.4.8. That's VN. What do we need? We need 5VN. How do we find 5VN? Because we need to find what is 5. 5V is equals to 1, again, because this criteria was met. So 5V equals 1. This one, this up here. It is in the shear yielding state. No buckling takes place, so 5V is also 1. So again, 5VN is equal to 1 times VN, which is 184.8, and it remains the same. They have rounded it up though to 185 kips. All right. So that is the design shear strength of that particular beam. We now need to compare it to the load acting, the shear acting on the beam, this VU. So we now need to calculate VU. VU class is nothing but the ultimate shear based on the loads acting. All right. From example 5.6, which we are doing, I'm going to bring down this again so we can see the loads. Right. From where are we? Down here. All right. From example 5.6 class, which we are doing, W, which is the ultimate load, is equal to 2.08 kips per foot. Let us find out ourselves. Let's calculate ourselves. Let's do it now step by step. What is the dead load? What's the dead load? You're going to calculate from where I write. What's the dead load? Dead load is equal to what? Equal to 0.4 kip feet, right? Kip per foot. Kip per foot. We are converting the pound per foot to kip per foot because that's what the units work with. So I convert this to this. 0.4. And what's left? Class are going dormant. Where's the class? What's the life? Class? The life is equal to 1.0. 1.0. Are those correct, class? Class?
Yes, sir.
Sure? Okay, fine. No, the next thing is to do what? Do the load combination. The load combination is what? 1.2 dead plus 1.1, sorry, 1.2 dead plus 1.6 live. So it's 1.2 times 0.4 plus 1.6. I want to move away from this state where I have to do this. Answer. What's the answer there now? That should be 2.08. That's where that 2.08 come from, class. For those who are going to the exam plan might be wondering where did that value come from? It's from the load combination that we have to do when we have only live and dead load. Somebody please verify. 1.2.
Yes, sir. That's what I got.
Huh?
That's what I got.
I don't get that.
I said that's what I got as well, the 2.0.
2.08. Okay.
Yes, sir.
So that's 2.08. And what the unit? Hip
Tips.
per foot. All right. That's the ultimate load. That's VU. No, that's not VU. That's the ultimate load. We need to use this load now and find VU. All right. Now, for those who don't remember anything about analysis, let me jog your memory a bit. We have a beam. We have a beam class 45 feet long and it's simply supported like that. That's a support. That's not a load, right? That's a support. I'm just trying to do a quick sketch. That's a support, and this is all of 45 feet. 45 feet. To beam. If that is too large, let me make it smaller. Let me change the color of this thing. All right, that's a beam class. Let me drag these up so get some space. The beam has a uniformly distributed load class like that. And I want vertical, right? Fine. It has a uniformly distributed load that it carries like that. And that load at the combined stage W. I'm not going to put level on dead load. I'm going to put the combined load here. W equals that value. And that included the weight of the beam. All right. So let me say W equals, for those who are making note and I want them to follow clearly what W means. W is when you find the apply the factors, right? So this is your beam class. 45 feet long with a factored load, a combined factored load of 2.08 kip per foot. Now, we are aiming at finding the shear. The maximum shear force class occurs at the supports and has a value equal to that of the reaction. Wrong or right? I am pulling you back to what you should have done in structural analysis or advanced analysis.
Yes.
You have a simple supported beam with a uniformly distributed load. The maximum shear force happens at the support, at the point of the support. That means that support A and support B. I am going to go even further by calling them RA and RB. I want to be as simple as possible. RA. I mean, this was from last school year, but let's take the time and go through it now, because you won't be able to do share unless you know this. All right, and this is now B. RB. All right. I'm saying, or what to speak to is that the shear force, the maximum shear force V, and by the way, class, why does the moment diagram for that thing look like a parabola looking like that? Remember that diagram? That's the moment diagram. The shear force diagram for this will look like this. It cross at 0 right there. That's the shear force diagram for that. Let me change the color. That's the shear force diagram for a beam like this. Where the I'm going to be as precise as right. The shear force diagram for a beam like this. The shear force is 0 at the middle of the beam where the moment is maximum. For those who know the relationship between shear and moment, the shear force is nothing but the first derivative of the moment, or vice versa. Right? So when the limit of shear force equals 0, then the moment is at its maximum. There is a relationship between shear and moment, and that relationship is actually taking integration. Integrate using the limits. But we're not getting to that. What we know is that the maximum shear force on a simply supported beam carrying a uniform distributed load occurs at the supports at these 2 points. It is a linear relationship. All right? And that value is equal to the value of the support. So if you know to find this reaction of a beam carrying a uniform load, then you already know the shear force. How do we find the reactions of a beam carrying uniform distributed load? Like this. But remember.
So I think you'd convert the UDL into a point load and
right.
Analyze it as.
And how do you do that? How do you convert this UDL into a point load?
Times it by half the span, I think.
Huh?
By half, multiply by half the span.
No, wait, hold on. One person said,
Yes,
convert this UDL into a point load. And my question is, how do you convert all of this UDL into a point load?
Right, sorry, you hear what I'm saying?
Go ahead now.
Right, I'm saying I think you multiply it by what's that? 2.8. I think you multiply it by half the span.
No, let's go. If you are converting this to a point load, it can be multiplied by half of the span. If you're finding the reaction from this, you multiply by half of the span. But if you're converting all of this to a point load, you have to multiply by all of the span.
Right, sir.
Huh? Are you following? Class, are you following? Remember, the idea of this class is not to teach this. This is really prerequisite knowledge coming to this. But let's go again. What does 2.08 kips per foot mean? What does it mean in real life? What is the idea of 2.08 kips per foot? What that means? No, man, no. What? No. I want an explanation. What does that mean? 2.08 kip per foot. What does that mean, really? Perfect. For every foot that we measure, if you should take it off and weigh it should weigh 2.08 kip. Then all right. Then if for every foot weighs that, and I have 45 feet in all, what do I need to know the total load on this beam? Huh?
Multiply by the total length.
Go now. What do I do?
You multiply the UDL by the total
good.
length.
Good.
Span.
If for every foot it weighs that, then for 45 foot it has to be 45 times this. All right? So we're getting somewhere. Which is why this says W times L. All right. So if I multiply this times 45, it brings me to an assumed point load in the middle. That's what it does. This times that convert this thing in as if it were a point load in the middle with a value of 90, whatever it is. All right. Now, if I have a point load in the middle and I have two reactions carrying it, what is the sensible thing to do to know how much each reaction, much support carry?
Divided by 2, sir.
Divided by 2, because it's in the exact middle. If it were at one side now, then it would be a different scenario. But because it is going to be in the middle, because we actually convert a uniform load to a point load, then it's going to be half of this point load. Class, that is what takes place over here. So it's WL to bring it to a point load, divided by 2 because of half comes to the reaction. Are we seeing that now, class? Did that explanation over here make this easier for those who had seen this and didn't know where it come from? Class?
Sir, you did it. I understand it now, sir.
You understand it now?
Yes, sir.
Anybody else? Anybody still in doubt how they came about this? No, we don't want the point load. We just virtually do something that brings it to a point load so that it can be easier. You can easily relate to it. But for some people who knows analysis, you don't need to do that. You could just multiply this by half of this, which in essence is this. It's really bringing it to a point load in any case, you know, because a reaction is a point load. Wrong or right? A reaction will read Kips and not Kips feet. Because as long as I multiply this by anything to do with feet, this feet is cancelled because this feet was under the denominator. So it's really bringing to a point load. But we are saying that what this is doing in essence is saying, okay, fine. If for every 1 foot, let's say these red lines was 1 foot, right? Each time I move 1 foot, if I should take this out and weigh it on a scale, I will get 2.08 pound. Kips really. That's what it means. So if I have 45 of that, it means 45 times the unit weight will give me the total. And that total will be like a point load acting in the middle. Let me see if I can explain. You take a book. Where is the center of mass for that book? The book is rectangular. Where is the center of mass for that book? Huh? Class, the person who asked the question. You take a book, for example. Where exactly on that book is the center of mass? Huh? In the center of the book. Because the book is uniform. It's a uniform thickness, uniform length, uniform height. The same thing with the load. The load is a uniform distribution. The load is rectangular like that. So the center, the load acts at the center. The mass act at the center of that thing, which is what this does. Which is why I said, okay, fine, we can really convert this into a concentrated load which acts through the center of it. Is that clear now? Good. Now that we have a load in the center, now that we convert that, so let's say we have converted that to this by multiplying, and the value now becomes 46. No, it becomes whatever that is. Let's work it out and call it PU. Let's call it PU. If I multiply 45 feet times that, what do we get? Somebody give me the value. What do we get? 45 times is 90 something. 90. Huh? 93.6. That's 93.6 clips. Feet gone now because the 45 is in feet. Good. That arrow class, this arrow, I'm going to change the color something else. I'm going to make it thicker to thick now. That arrow class represents a point load coming from this. And it's done this way because you are now able to see it quicker. Because it's not logical that if I want to find RA, I can now say, but if this in the middle, it's a symmetric load arrangement. That means obviously half of this comes to this, half goes to that, don't it? That's why they virtually bring this up point load, you know, so that you can quickly see that, hey, but it can't go no other way. Half must come to this, half must go to that. All right. So once you have this, then you can say, okay, fine. RA is equal to this divided by 2. RB is equal to this divided by 2, which is what this over here is saying in one step. W times L is the same thing that we did right here. W times L. Give us that. And divide by 2 is because we have 2 support, so half goes to this one, half goes to that one. Same thing in one step. I am taking the time to go through this so that for those who don't understand how this just jump to that, it can now click there. So this is what happens. This is the illustration of what happens there. Again, go read up on analysis, because this is the simplest beam analysis you ever have to do. All right, so let's leave that now. So we now know how to find VU. So VU is equals to this, which is this divided by 2. All right. So this is the maximum shear acting on the end of the beam. But the beam can what? The beam can carry all of this, don't it? The design shear strength of the beam is actually 185 kips, but only 46 is acting on the beam. It therefore means that the beam is way satisfactory. Is that good, class? Any questions about that? Any questions? Class is rather silent. Let me see what it's inside. 14 people in class. All right. Any question before we move to another example? And the same thing, class, would have been done with the ASD method, just that your VA will be coming from AA, and you'll be using a factor of 1. 1 times dead load plus 1 times live load to give it. But the principle remains the same. The B will still comply. Any of these two you use. All right. Can I go to another example which sheds some more light? And also have you do this calculation yourself? Good. So let me clean up this. I forget. Clean up this. I'm going to find another example in another book, which maybe we should do this one. Okay, fine. So here's a okay, perfect. Here's a good example. All right, I might as well make a sketch for this also. It says here a W16 by 89 beam with a yield stress of 50 KSI is simply supported over a span of 20 feet. The beam is 20 feet long, class. Let me make a 20 feet long sketch, like I did earlier. All right, fine. So this beam is 20 feet long. 20 feet. All right. So as not to confuse anything, I want to change some colors. All right. So the beam is 20 feet long. All right. It's a W 16 by 89. So we want that down here also. W 16 by 89. All right. W 16 by 89. It says here, it carries a uniformly distributed dead load of 2 kips per foot, and that includes the self-weight, and a uniformly distributed live load of 6 kips per foot. All right. So I'm going to draw something representing the loads. I want to change the color. I want to do this. I want to no, that too pronounced. All right, fine. All right, fine. So let's copy these now down there for ease and quick reference. All right, fine. So that as that. So dead load is that inclusive of a self-weight of the beam, and this is live load. All right. Oh, what's that? All right. So see this sketch there? That's the beam. And of course, we know that Fy equals 50 ksi. These are all data that we need to have right at our fingertip. All right. So those are all data ready to go. We have that sketch, class. We have that sketch.
Yes.
Huh? Okay, fine. Now, the question is, determine if the beam is adequate for shear. So the first thing we need to do is to check the web for slenderness, right? The first thing is to go and find H over TW. Again, this is the W1689, so we go to our manual, and now that we're going with W14, let me delete all these red lines. I'm looking for W16. W16 should be above W14, so I scroll up. All right, so let me get rid of these out of my book. W14, we're looking for W16, W6, fine. So W1689, W18, W16. Okay, fine. So W1689, here goes. So this is W1689 on the dimensions page. That's dimensions. And I need to find W1689 under the. Okay, fine. So it's 1, 2, 3. The 3 is stock number 3 from the bottom. 89. This one. Stock number 1, stock number 2. All right, fine. So this one. All right. So I have identified my W16 in both dimensions and properties. All right, fine. So we want H over TW, which is this from properties table. All right. H over TW is equal to 27. H over TW is equal to 27. All right. Now the remainder of it is calculation. 2.24 times the square root of is the same square root. This one square root. They have only used a different method of doing it. Raise it to the power of a half. Or you say I say square root. However, it works out to be 53.95. All right. The thing says if H over TW is less than this value, then the beam the web is not slender and it will fail under yielding, which is what this says up here. Let me get back to it. This is what this says up here, right here, case 1. Therefore, if that happens, then CV1 equals 1, 5V equals 1, and omega V equals 1.5. So it did happen in this case, and which is why they said 5 is equals to 1, omega is equal 1.5. And CV also is equal to 1. They did not write that out. And that is why the nominal shear is equal to 0.6 FV, sorry, 0.6 FY times AW CV1, which is equal to 1. But them drop it up because equal to 1. All right? And that gives us a nominal shear of 264 Gibbs class. That is from the material of the beam itself. 264 Gibbs. Now we need to be comparing the design strength. This is nominal strength, so we need to calculate the design strength next. The design strength is equals to phi times Vn. Phi is equal to 1, as seen down here, so it remains the same. Now, the big part is for you. We have just gone through an example. I want for you independently to calculate the VU, the strength, the shear acting on the end of the beam. Based on what we just done a while ago. By the way, these are not factored. These are unfactored loads, right? These are unfactored loads as is right now. Do not confuse them with W. Right now, you're seeing WD means unfactored dead load, and WL means unfactored level. When you factor them and add them together, they become WU. Know the difference. So, class, I want for you to calculate and tell me what the shear forces or the reactions are. What is VU? You can tell me while doing it, or you can do it independently, individually, and then tell me. But for now, that is exercise. Let's not take too long. Time is almost exhausted. Any answers yet? Any answer yet? All right, I'm going to do this quickly. And so that when you have your answer, I can compare. 1, 2. All right, I'm done. No. Any answers yet? Any results yet? Sorry. Wait a minute. I'm waiting. Any results yet? Huh? Oh, we want VU, the shear acting on a beam. Remember, we need to compare VU with 5VN. We already calculate VN and can easily find 5VN. So we need to compare. We need to reach. We need to get to this. Huh? No. We need VU so we can make this comparison because we already have this value 5VN. So we need VU. VU is coming from the loads acting on the beam. So we need to calculate that. That's not in the table. What do you get? 120. Okay. Anybody else?
Sir, I got the same thing.
You got 120. Why songs are not that? Anybody else? Okay, fine. So 120 is the answer. And this is it. See it up here. The factored load W is equal to 1.2 WD plus 1.6 slab, and it works out to be fine. So this is it. When you combine the loads, and VU is a factored shear. Same thing I would say as the support, reaction support, or reaction, which is given by WL divided by 2, which is 120 kips. So the beam must be able to withstand 120 kips at the end. All right. Now, how much can the beam withstand? The beam can withstand 5VN. VN, we already know, was 264 kips, and phi is 1 because the web didn't buckle. So from this narrative here, right here, no buckling take place because this compliant. So phi equals 1, and that is why this one is right here. That is why 1 is used right here. So 5VN is equal to 264. 264 is way more than 120 kips, so the beam can satisfactorily resist shear. Now, very interesting. Remember when we did moments, we also went into the manual to find moments for beams. You can also go in the manual and find the shear for beams. We calculate it to be 264. If we go into the manual, table 3-2, I'm going to see if I can quickly find that table. Table 3-2. All right, fine. So we are 3.6. I'm moving too fast. All right, fine. Remember, we use this book to find moments, right? And to select a member. The same table can be used to find the shear force of beams. If you look to the extreme right, see here, see there, 5VN or V over omega V. So we are using the LRFD. So we just need to find our particular shape. Our beam is W, let me see the size again, W 16 by 89. So we're looking for W 16 by 89, 16 by 100, 16 by 89 here, W 16 by 89. So we move over and see it says 264. Sorry, 265. All right? It says 265. We have calculated to have 264, but not so bad after all. Right? So we can use a table or we can do the raw numbers like we did right here. All right? But doing this way is much more practicing, especially for those who right. So that's it for share, really. Share doesn't go past that. The only thing is that we are lucky so far to have two cases that brought us to this. If we have a case that brought us outside of that now, we'd have to now go and use up these. I might force to find out an example for tomorrow morning. I will do that first and then move on to connections. All right? But that's where share really stop. It doesn't get difficult than that. That's really it. It's easy to check the web if it buckles. If it don't buckle, then you know you're in case one. And simply this applies. All this apply. If it buckle, if it's more than this, then you know you move to case 2 and you have to calculate these to see what CVI you must use. And that's it really. It's a matter of comparing the nominal design share really 5EN versus this.
But sir, for the other one, the other case, it would be for I shape though. I think that's what I thought.
All of them are for I shape.
Okay.
All of them are for I shape. It says when it says when the, let me see if I can read it again. This one. See there for all other I shapes. So there are some I shape that fall within this. It said most. It said most double shape, which is same as I shape. Most double shape fall within this. But for others that don't, then you use up these. You get it now? So if you do a calculation for an I shape and it does not comply here, it means it's no jump into this one. Right away they gave us these two values, but no CV, because CV is also subjected to other checks. So we have to do other checks to find what CV value we must use. I would find ourselves in one of these down here. Okay? I will
Okay, sir.
I will go through tonight and maybe create a scenario. Find a scenario where that happens. All right? So we can look at that. But that's really for shear. Shear does not get anywhere past that for simple beams. Shear doesn't get past that for simple beams. Which is why last week I wasn't worried to rush into shear. I spent the time to look at what we looked at. Because this is something that they can cover in one class, really. Which we did. All right. So that's where we end class. This is chapter 5 of the Steel Design 6th edition, and it's 5.8. For those who want to go back over, including the first word exam. All right, 5.8.
Sir, before you go, I have a question about the assignment I forget to ask last week. So for the one of the questions, I would want to know, like, for the AE, when do you assume AE equal AN? And when do you just go ahead and use a share lag factor?
No. Well, let's go there. Your question is, when do you assume AE equals AN?
Yes.
Wait, no, but there's no way that we should assume that.
Okay, so sir, in the question.
Okay, fine. We did some word examples that they made those assumptions, right?
Yes.
Right, and I did say that those are, and some point they actually say assume AE to be 0.85 AN, remember?
Mm-hmm.
Right, and I'm saying, and I did clarify that the author would have done that because we did not get to the point of knowing how to calculate AE yet.
Okay.
Right, so know that you know how to calculate AE
mm-hmm.
using the different cases, whether you want to be 3 balls in a single line or whatever, or you want to be an angle or a plate. You know that little table?
Yes.
That teaches you how to calculate X bar minus 1 over L, whatever the case may be. That little table having all on things. That's
Yes, sir.
what teaches us to calculate AE.
Okay. Okay.
All
I
right.
just wanted
So
to
right, fine.
clarify.
So having subtracted the bolt O and all that to get AN and then use AN to find AE, applying a factor U, right? Is it true that U is equal to that AE is equal to U times what? Shear log times what? AN.
Yes. Yes,
Good.
sir.
Good. AN
Yes.
you know to calculate because AN having to do with removing calculate taking away the bolt and tolerances, right?
And the
And U is a
tolerance.
shear lag factor, which depends on whatever case you find yourself in with your particular design. So
Yes.
so
Okay.
AE equals to UAN.
UAN. All
Where
right,
we just
sir.
all right, so that's maybe one formula you might not you will not see on a formula sheet. Can tell you from now.
All right.
Good. It's something like that you shouldn't really be telling you. It should really be sticking with you. All right. But yes, there's no case that you should really be assuming it. Even if you work out to be 1 when you're looking at the table, you must always know that AE is equals to AN times U. Right? The reason is there is always something influencing the effective area of an element. When you weld beside an element, welding is a burning and fusing exercise. It burns out portions of the material. You know that, right?
Yes, sir.
Good. Which is why the effective area is no longer, which is why the area is no longer the real area of the element, because the welding
Yeah.
caused part of it to be burned out. Similarly, when you drill holes in the thing, then the hole takes out some of the area. All right, and then now because of how the loads are applied across these welds or bolts, then the entire area of the element is not working. So shear lag factor is really having to do with how much of the area is really contributing to carrying the load. That's what shear lag factor is really compensating for. Especially for those angles where you only connect the angle by one leg, not the two legs. So even though
Oh.
that's what
Okay.
the theory says. You need to read over.
Okay, sir.
It's in the theory, you know.
Okay, sir.
When you connect an angle by just one leg, it's not the entire area carrying the load, really. Most of it is gone to where the connection is made.
The connections. Yes, sir.
Okay. Read back. And you see all that.
All right, sir. Thank you.
But yeah, you do not need to assume
Anything, just
AE. It's calculated.
okay.
You just need
All
to
right,
know,
sir.
be able to interpret from the sketch you see there. What case are you
Which case?
Are you
Okay,
in?
sir.
All right.
All right.
Any other
All right,
questions?
thanks, sir.
That was a good question. Any other question? By the way, we'll be doing this again tomorrow. This AN and thing. You know why? Because when we do simple connections, then for tension members, then the strength of the element is not going to necessarily be the deciding strength of the design of the connection. You have to check the element, check the wells, and check the plates. So whichever one comes up with the lower strength, then that's what determines the ultimate strength of the connection. So you'll be getting the opportunity to do this again, really. When we do connections tomorrow. And I can tell you there's a question.
Sir.
And I can tell you there's a question on the exam like that.
On the exam. Okay. I'll make
Right.
a note of
Because
that.
that question would basically cover two things: members to tension plus connections. All right. All right. All right. Let's not delay any further. Let's go have our evening rest so you can come tomorrow morning early and take on connections. All right. Good evening, class. See you tomorrow.